This lecture focuses on the role of the petroleum engineer and also on inflow performance through the understanding of the pressure losses in the tubing, the reservoir, and the surface facility. Production engineering is really part of a larger group referred to as petroleum engineering, which attempts to maximize production or injection safely and cost effectively. Petroleum engineering is subdivided broadly into reservoir engineering and production engineering, which sometimes called artificial lift structures. The reservoir engineer would focus on the reservoir in terms of the porous medium, storage, and also the flow characteristics of both the fluids and also the rock matrix. Production engineering focuses on the well losses, pressure losses, all the way up to the wellhead and then onto the surface gathering systems, which would entail or be consist of like separators, flow measuring devices, and pressure measuring devices, sand detectors, and then onto the storage facility where the product is physicalized and treated for sale. So the petroleum engineer benefits from an understanding of the geology, which it would include the fluid migration and accumulation, and some reservoir engineering in terms of how the fluid actually flows through the reservoir. And all of that helps the engineer to perform their core role more competently. So the petroleum engineer or the production engineer needs to interface closely with the reservoir engineer, the facilities engineer, management and finance, well operations, and the G&G group, which would include geologists and geophysicists. The reason why one would need to be liaising with management and finance, it's two reasons. One, you, you need money, access the money to perform certain work to increase and maintain production. And two, you need to ensure that what you're doing is in fact returning making a good return to the company. And also, especially like Trinidad, which is a gas-based industry economy, invariably you would have gas contracts. So one needs to understand what the demand is so that one can ensure that the delivery meets or exceeds the demand. A key role for the production engineer is to understand how a well is performing, and the production engineer would do that through different surveillance type techniques. Very basic one would be understanding rate versus pressure drop along the flow path. Um, Understanding the pressure drop in the reservoir, whether or not there's any kind of additional skin effect, and do that type of surveillance. Well testing, which evaluates the reservoir performance and also how the well is actually delivering the fluids from the bottom of the well to the surface through basic well testing, which is routing a well to the test separator and measuring the rate and the flowing bottom hole pressure, and also through another technique that would be used would be production logging, running PLTs to to determine what what um, contribution is coming from which part of the reservoir itself. And having understood or gotten enough information to conclude what might be taking place, that then leads the production engineer to develop strategies and programs to optimize, enhance, um, remediate the well, and so lead to improved performance both from an inflow, from a well, from a surface perspective. A simple production system for those who have not been exposed at all to the oil and gas industry, what you would have is at a high level, you would have the reservoir, and we would be looking at equations that would describe the pressure losses within the reservoir. Then you would move through the completion, the different types of completion, through the perforations, through the screens, through the gravel pack, what you may have down there in terms of from a completion standpoint. And then you would look at the well construction itself in terms of the pressure losses that would take place in the tubing. And the tubing would have different types of jewelry, nipples, profiles, subsurface safety valves, other restrictions. Then you would move to the wellhead where you would also have some pressure losses, and then through the choke, which is like a spec break, to the flow line, some separators, and you would then have either goes to stock tank, and you have gas coming out the top of the separator. So what I would like to do is now introduce you to a concept of nodal analysis. And what that allows you to do is to solve two simultaneous equations to determine at a point along the flow stream and therefore work out a unique solution. And the whole concept is, what is a node? Any point in the well can be considered to be a node. And what you would want to do is to, as I said, both upstream and downstream be able to find equations that describe those and then solve. Because at the node, the rate into the node is equal to the rate out of the node, and only one pressure can exist at that node. Typical production system with nodes. You can have nodes typically within the reservoir, the near wellbore region, within the wellbore itself. You can do a node at a restriction, so you can understand the pressure loss that might be taking place across that restriction, and how would you optimize that. 4 being like a downhole nipple, 5 would be another nipple or a subsurface safety valve. Up on the surface, number 7 would be like your choke. 8 would be within your separator and the back pressure on your separator, and if there's an opportunity to lower that, and what impact it will have on your overall system. And then 8B would be your stock tank. Some of the losses are indicated in diagram there. Yes, let's take a look at pressure losses in the tubing itself. But before we do that, let's look at the overall pressure loss from the reservoir all the way to stock tank. And from the boundary of the reservoir, the drainage boundary where the reservoir pressure PE all the way to the near wellbore region, you would see there would be some pressure loss associated with the fluid moving from the outer end all the way to the near wellbore region. And just close to the wellbore, there's a significant pressure drop that takes place as you move through the completion. And that brings you to PWF, which represents the reservoir, flowing bottom hole reservoir pressure. And from there to PWH, that's the pressure loss that would take place in the tubing itself, which we're going to talk a little bit about a little later on. But from the wellhead, you would have a significant pressure drop there across the choke. So that's what that big pressure drop represents. Then the flow line, again, the flow lines are normally sized so that there's little or a small amount of loss due to um, um, hydrostatic, simply because they are invariably on the surface, and even though there might be some changes in terms of elevation, is not normally as significant as the well itself. And then from the separator to the storage tank, there would be losses associated with that friction in the flow line. Okay, so let's zero in a little bit on the pressure loss that takes place or might take place in the tubing. And we would look at three different types of fluids: single phase, liquid, dry gas, and then two phase oil and gas. So let's look at A, which is liquid rate or single fluid. The wellhead pressure on all three would be the same. Um, that's an indication or represents the system pressure, and that would not necessarily change unless you did something on the surface, like some kind of debottlenecking in terms of removing some restrictions, using larger flow lines when they tend to restrict flow. But in most cases, that is going to remain constant. Um, and Coming back to A, the single liquid, you would see that the pressure loss attributed to the hydrostatic head is fairly significant, and that's because because of the shear density of the fluid, and the hydrostatic head is given by H rho g, rho being the density of the fluid, and the H is the height. Um, and the other component that makes up the pressure loss would be due to friction. And as the liquid rate increases, you move from laminar flow to transition and ultimately to turbulent flow as the rate increases. And as you can see with turbulent flow, the change in the slope is increased, and that's because with turbulent flow you have more pressure loss attributed with that type of flow regime. If one was to look at B, which is dry gas, you would see that the wellhead pressure again is the same as before. The difference now is that the hydrostatic head is lower because the density of gas is lower. And then the other component, which is friction, it's much more prominent because with gas rate, especially as the rate increases, you are in turbulent flow, and so you will have a significant amount of friction taking place. The last one, C, which is two-phase oil and gas, you would see that the hydrostatic head is not as high as the pure liquid rate, and that's simply because the gas actually makes the density of the fluid a little lighter, and there's a change in the friction as you move um, um, from pure liquid to a two-phase fluid, which would be gas coming out of solution, and you have that segregation and slip and hold up taking place, and so it changes the way that friction affects the pressure loss. Um, in general terms, depending on the orientation of the well, for a vertical well, elevation would account to 85 to 98% of the pressure loss, with 2 to 15% attributed to friction. And for horizontal well or flow line or pipelines, the elevation is normally the pressure drop attributed to elevation would be between 0 and 30%, and friction 70 to 100%. In summary, we have looked at the role of the PE, optimization of production and cost within the boundaries of HSE. Safety is good business, and so we always need to do or to be safe in whatever we're doing. We looked at inflow performance or IPR, which talks to the pressure loss and flow within the wellbore. And then we introduced tubing performance, which focused on pressure loss as a function of single or multi-phase flow. These tubing performance curves can be also referred to as flow in traverse or J curves. And we talked a little bit about nodal analysis, which is a method employed to carry out initial designs for monitoring and for evaluating opportunities to enhance or do remedial work on wells. So what's next? In our next discussion, we will look at Darcy's equation as a start and investigate other relevant equations that describe steady state, semi-steady state, and pseudo-steady state flow. I have also included a short video on productivity index for your understanding. Until next time, be safe and inquisitive. Bye.